So hello to all of our panelists and to our audience. My name is Griffith Couser. I am a policy officer until the end of today, as it so happens, at the European Polar Board. The European Polar Board is a membership-based organization representing the polar programs of 31 different national research agencies, universities, and funding agencies across the European continent. And just so that everyone is very much aware, the webinar is being recorded and it will be available on the European Polar Board YouTube channel after the webinar. So a bit on ocean ice. Ocean ice is an EU-funded research project. It's focused on measuring and understanding the interaction between polar ice shelves and the polar oceans. And the project is aiming to add data and understanding to the underlying processes in this dynamic. But we have the project coordinator, Dr. Ruth Mottram, who can, of course, speak in much more detail about the project than I can. I'll say the European Polar Board participates in Work Package 9 of the Ocean Ice Project. That's project coordination, dissemination, and outreach. And as part of this, we're conducting this webinar series, which will feature all of the ocean ice work packages. And all of these webinars will be available online as a long-term resource. So work package 3 is ice sheet mass balance, forcing, and dynamics. It is led by Dr. Ruth Mottram from the Danish Meteorological Institute, and she will talk about the work package's ongoing work, expected outcomes, and desired future impact. She's joined by several other project researchers with the work package, and I will allow her to make the introductions. But before I throw to her, I would like to tell the audience that you can ask questions in the chat or using the Q&A function. And once the speakers have gone through their presentations, we will have a short Q&A session. So for any more information about the project, we will put a link to the project website. And with that, I will give it to Dr. Mottram. Thank you very much. I think you're still on mute.
Okay, thank you very much, Griffith. And I was just saying we'll be very sad to lose you from the project. I hope that you can see my screen okay. Yes. Can you see also the window where I'm talking? Perhaps I should remove that too. Yes, sorry, I've gone too far. I think you've actually said many of the things I was going to say. We're very happy and honoured to be allowed to share our work. The Ocean Ice Project has been going for a couple of years now, nearly a couple of years, and we're very happy that we got this project. It's a very large project from Horizon Europe and many partners involved, and it has a very broad range, including a field component and a modelling component and also an Earth observation component. And we're going to try and cover all of that in this talk, and it will not just be me. We have many other people. I wanted to quickly give a little overview of ocean ice. We are looking very much at Antarctica, which is in the center of this picture here, but it's also about the impact of Antarctica on the rest of the world and the rest of the world on Antarctica. So we're looking at the ocean and what's happening with the ice sheet there. As I mentioned, we're looking at all sorts of different features here. Modeling, satellite data, lots of in situ observations all the way around. I'm very happy that we've managed to get one of our new Ukrainian partners in, and they will help close the gap here on the Antarctic Peninsula, which was not part of the original plan. So we are really looking at a lot of in situ observations, but also trying to integrate those with models and using satellite data too. So this is work package 3 that we're going to be talking about here, and we're very much focused on the ice sheet here. All the different things that are happening there, the surface processes, the ice shelf processes, and the calving of the icebergs as well. And I just want to highlight here that we have many channels to share our work on, and please feel free to follow us on any of those to hear more about it. So as Griffith mentioned, this work package is about mass balance of the ice sheet. It's about forcing factors, and it's about dynamics. And what do we mean by that? We mean surface processes, the sun here melting. We mean snowfall. We mean ocean processes and the interactions under the ice shelves that fringe Antarctica, and really trying to get a better estimate of the ice and incoming mass from snowfall, but also the outgoing fluxes, the snow melt, the ice melt, and the calving. And so today, to highlight this, we've got representatives from just 4 of the partners who are all working in Work Package 3, but also in other parts of the project. Elizabeth Case is going to give us an introduction to snowfall and snow melt, the components of what we call surface mass budget. Gaël will give us a talk on ice shelf melt and calving, and how we can use satellites to assess the kind of fluxes that are leaving the ice sheet this way. Keith from BAS will talk about ice shelf basal melting, and he's got some really interesting in situ observations to share and to kind of think about the implications of those. And then finally, Anastasia from the National Antarctic Science Centre will talk about some work that is planned. And I should mention at this point that ocean ice has been going a couple of years, but we recently got hop-on funding from the Widening Access Programme from Horizon Europe, which we were extremely happy to get. And this meant that we could bring in the National Antarctic Science Centre from Ukraine. And Anastasia will be working within that framework, looking at extreme events and how this will potentially affect ice sheet mass budget processes. So I'm going to stop there, and I'll ask Elizabeth to share her screen, and she'll be the first speaker in the thing. So please do go ahead, Elizabeth.
Thanks so much, Ruth. Is that like good? Does the screen look good?
Yes, that's perfect. And maybe you'd like to introduce yourself first. I'm sorry, I should have done that.
No, it's all right. It's all right. My name is Elizabeth. I'm a postdoctoral researcher at Utrect University at the Institute for Marine and Atmospheric Research. And today I'm going to talk a little bit about the work that I've been doing for the last few months, looking at fresh water from the surface of the Antarctic ice sheet. But kind of in order to contextualize this, it's useful to think about sort of the broader picture here. So I'm sure most of you attending know that ice sheets are losing mass quite quickly. So this is looking at sort of the last 30 years of mass in Antarctica. The red line is the whole ice sheet, and basically down means that the Antarctic ice sheet is, or this is the peninsula, and then we have purple is the Antarctic ice sheet. And then, yeah, as you can see, Antarctica is losing mass, and a big question is, where is this mass loss coming from, and where does it go when it enters the ocean? So most of the mass loss from both ice sheets from Greenland and Antarctica are coming from around the warmer, wetter coasts. They're at lower elevation, and the ocean is a big pool of heat, basically. So we tend to have more like high accumulation and wetter, warmer conditions around the coast. And this is where most of the meltwater is coming from. And also this is where the ice sheet is most connected to the ocean. That said, while we can observe where we're losing mass from today, there's a wide range of possibilities of what mass loss from Antarctica could look like in the coming century. And a big part of what ocean ice is doing is trying to assess what those uncertainties are and better connect the ice and oceans. And yeah, that's kind of the crux of this work. So where does the ice that melts, where does it go? And then what impact does it have on the oceans? So what happens with the ice matters for the ocean. Glacier, snow, and ice is fresh water, so it's not salt water. And this means that it's more buoyant than that salty, dense ocean water. And as a result, it tends to act like a cap. So that buoyant, cold, fresh water that's coming, that was solid ice and now is liquid, it kind of sits on top of the denser ocean water, and this starts to change ocean circulation. And so vis-a-vis these density differences, the ice sheet melts and blowing snow. So that snow that's being picked up and carried out onto the ocean, this can affect ocean circulation. And so one example of why what happens with the ice matters for the ocean and why we care about all of this fresh water that's kind of entering the ocean from these ice sheets is because of large ocean circulations like AMOC, which stands for the Atlantic Meridional Overturning Circulation. And AMOC is basically a giant heat pump. It's a conveyor belt of heat that takes warmth from the sort of tropics and brings it north, and then cold water travels south. And fresh water from the Greenland ice sheet can reduce this circulation by kind of reducing that overturning that's happening in the north. And so we really care about where that fresh water is going and how it's interacting with the ocean, because it has truly global implications. And so, of course, what happens with the ocean also matters for the ice. So there's this kind of two-way coupling. There's a real relationship here. What happens with the ice matters for the ocean. What happens with the ocean matters for the ice. And that's really what this entire project is about. And of course, because the ocean is it connects all of us together, what happens with the ocean and with the ice matters for all of us. So there's real implications for coastal cities and like mitigation and adaptation policies as a result of these changes. So I'm going to talk through some of the sources of glacial fresh water. So this is how ice is getting into the ocean. So we have what we call calving, which is the breaking off of large icebergs from the from the, I guess, like the coast of the ice sheet. So you have glaciers that run into the ocean, and then icebergs break off from the front, and they can travel out and bring fresh water quite far into the ocean. There's also the contribution of melt from underneath glaciers. So as a glacier flows, the ice creates like friction against the ground. This causes melting. There's also geothermal melt, as well as pressure from the weight of the ice itself. And then finally, there's these surface processes. So this includes melt from the sun, literally heat from the sun, melting snow on the surface. Rainfall, which doesn't happen very much in Antarctica, but it does happen a little bit. And it's a question of where that water is going and whether it stays on the ice sheet or not. And then there's also this weather wind component, which is where snow is picked up from the surface of the ice sheet and then blown into the ocean. And that's really what I'm going to focus on today. So melt and rain, we kind of lump into this grouping called runoff. So not all melt and not all rain that occurs on the ice sheet makes it into the ocean. Some of it refreezes into the ice sheet, but a lot of it does end up running off as liquid water. And so we need to gauge how much fresh water we're getting from the ice sheet surface in order to sort of get a sense of what the contribution of those three components, the icebergs, the melt from underneath the glacier, and these surface processes, what those various contributions look like. And one way that we do that is by looking at different models. And so we're not trying to say whether or not one of these models is doing better than the other, but rather use all of the outputs from these atmospheric models to kind of quantify the possible range of freshwater production. How much ice is melting or being blown off or arriving as rain and trickling off the ice sheet today. So we can start to take a look at those results. So this is looking at the rain component. As you might expect, there's not that much rain in Antarctica, but there is a little bit in the Antarctic Peninsula. You can see the little blue dots in the sort of grid northwest corner here. And then we can start to take a look at melt. So this is from this is heat from the surface melting the snow. And you can start to see that there's some variations in these models. So we have three models that I'm showing here, and we see that one here on the right shows more melt than, for example, MAR, which is on the left side of your screen. But again, what we're looking for is what the possible range of melt production is. And then finally, we want to know with rain and melt, how much of that is actually going to leave the ice sheet, and that's what runoff is in this case. So we see that most of the runoff is concentrated in the Antarctic Peninsula, but there's also little blue dots around the edges of the ice sheet So we're getting runoff kind of like around those coastal areas. And then the last component, as I talked about, is snow drift. So this is how much snow is picked up and moved around and then eventually is blown off of the ice sheet. So for this, we only have 2 models to look at what the range of contribution of snow drift is. And we can see that there is actually quite a bit of snow that's picked up and moved around the ice sheet. But what we really care about is at the edges here, if the wind is blowing off the ice sheet, how much snow it's carrying along with it. And that's our component of snowdrift into the ocean. And so there's this iceberg component, there's melt under the glaciers, and there's these surface processes. And the total freshwater contribution from Antarctica is something on the order of 2,500 gigatons, give or take. And we can see that there's quite a range of possible contributions from these surface processes, kind of anywhere between 11 and 500 gigatons a year, which is less than 1% to 20%. So really quite a range. And this shows that this is a process that we perhaps need to focus on understanding a little bit better, to understand where that water is going and really how it's contributing to ocean processes when it's reaching or when it's leaving the ice sheet. So in sum, surficial processes contribute to the yearly Antarctic freshwater output, and all together combined with iceberg calving and subglacial runoff, the Antarctic ice sheet outputs enough freshwater that it may affect local ocean circulation. And then truly the main takeaway is just that what happens to the ice sheets affects the ocean, what happens to the ocean affects the ice sheets, and what happens to both affects all of us. Thanks so much.
Thank you very much, Elizabeth. That's really good. I'm going to ask Gaël to continue now, and we'll talk more about the solid component and some surface melting, I guess. Go ahead, Gaël. We seem to see your speaker notes and not your, that's the one. Yes, thank you. But you're muted.
Now it should be fine. Sorry for that. Thank you, Ruth, for the introduction. And indeed, I'm going to speak about iceberg calving and melting and how we evaluate this quantity from Earth observation and satellite remote sensing. And thank you, Elizabeth, for the introduction and surface MESDA. Next slide. How does it work? Here it is. So Antarctica is clearly a vulnerable region and a truth of change. And despite its geographical remoteness, human activities are already affecting Antarctica. And the warming of the continent's atmosphere is now discernible. Warming of the southern ocean is leading to increased melting and disintegration of ice shelf and runoff from outlet glaciers, as well as accelerated loss of ice sheet mass in West Antarctica and certain eastern regions, contributing to accelerated sea level rise. So this flow of fresh water leads to a drop in the salinity of the surface of the Southern Ocean, which in turn affects its ventilation, stratification, mixing, and the formation of deep water. And since 2015, the extension of sea ice here in gray has retreated. So these changes are already having an impact on the entire Antarctic trophic chain, particularly the krill, and could have cascading effect on the functioning of Antarctica's unique and fragile ecosystem and biodiversity. So Antarctica is also a major player in global change. The response of the Antarctic ice sheet to global warming is currently the main source of uncertainty in projection of the amplitude and rate of sea level rise for the second half of this century and over the next few centuries, which could lead to a rise of several meters by 2300. And obviously, this is a major knowledge challenge for the sustainable management of our coastline. So the IPCC assessments highlight the limits of current knowledge about a number of key processes taking place in Antarctica at the heart of the interaction, the feedbacks, and the threshold effects that are still poorly understood and are a source of considerable uncertainty for climate projection. And notably the Southern Ocean, which today absorbs almost 2/3 of the heat and half of the anthropogenic CO2 absorbed by the world's ocean, play a key role in the coupling between the global energy balance and the carbon cycle. And the evolution of its storage capacity remain uncertain. And advancing our knowledge of change in the Antarctic is therefore essential to inform urgent and complex decision-making in favor of resilient development in the face of climate change. And ocean is a contribution in that direction. So based on this short description of the context, it appears clear that the change in the freshwater flux from the imbalance of the Antarctic ice sheet is key. Next slide. So this forces me to go into a little more detail about the dynamic of the Antarctic ice sheet and the concept of mass balance. So an ice sheet is formed by the accumulation of snow, which compacts to become ice and then flows under the effect of gravity from the interior of the continent to its periphery. It is therefore a mass of water that is stored in the form of ice on the continent, and a potential contribution to rise in sea level. And Antarctica stores about 58 meters of sea level equivalent. So in Antarctica, atmospheric temperatures remain low enough throughout the year, as we just see, for surface melting is still limited and sporadic, mainly on the Antarctic Peninsula, so that the ice on the continent begins to float on the ocean, forming ice shelf that fills the base. And now that I have explained the mechanism by which mass is gained, the ice sheet naturally loses mass, either through the calving of iceberg or through melting at the interface with the ocean. And once again, surface melting is currently marginal, but we know that it's clearly going to increase, which in addition to adding an additional source of fresh water will can weaken or lead to collapse of the ice shelf, as observed, for example, in 2002 for the Larsen B and on several other ice shelves since. And it's important to understand that the role of this ice shelf is fundamental. They hold back the flow of the upstream gradient ice. Without these ice shelves, West Antarctica will probably be unstable, as would several regions of East Antarctica. They would gradually collapse, flushing grounded ice toward the continent and contributing to a rise in sea level of around 20 meters over several centuries or millennia. In a way, these ice shelves around Antarctica are the safety belt of the ice sheets. So how can we quantify this flow of fresh water from calving or sub-ice shelf melting that influence ocean circulation and sea level? So for global repeated monitoring that is as continuous as possible over time, there is currently no other method than satellite measurements. It's not simple, it's not a direct measurement, and it requires a combination of various satellite products, the term in blue in the equation here, and modeling data in red. So don't be frightened by this equation, which is a mass conservation equation. What it says, if you are able to measure the variation in 8 at a point of the ice shelf using satellite altimetry, as illustrated on the left on the Larsen C ice shelf here, then these variations are equal to what is coming at the edge of the ice column and at the edge of the ice columns. And in terms of mathematics, it's what we call the ice flux divergence. And this is obtained through the measurement of the flow velocities, as illustrated on the right, using INSAR measurements. So this illustration shows you where we see where the channeling of the ice flow into ice streams. And if you further know the change in the density of the column and the surface mass balance as introduced by Elizabeth. So basically the accumulation of snow at the surface, to put it very, very simply and too simply, which both are given by an atmospheric model, you can deduce the term that is missing, the melting rate under the ice shelf at this location. Once we have estimating the melting of the ice shelf at each of its points, we can estimate the calving flux. This is the same type of equation, conservation of mass, but expressed for the whole ice shelf, and the variation in the ice shelf volume is estimated by the altimetry, as I said, and it is equal to what is lost at the ice shelf boundary, the basal melt that we just estimated here. The surface mass balance, again, from a regional modeling approach, the incoming flow in the ice shelf at what we call the grounding line, and the calving flow, which is what we want to estimate. So several products estimating the evolution of melt and calving rates over a period of about 20 years have been proposed in the recent years. And the essential role played by Ocean Ice and Work Package 3 for this work was to review the existing data, specialize the melt and calving rate, estimate, and finally compile a data set that could be used directly by ocean or ice sheet modelers. And you can see here an illustration here of the evolution of the rate of melting on the left and calving between 2000 and 2018 on the Pine Island glaciers as they were delivered to our partners. So what should come next? I believe there are three main points in order of importance, maturity, and to some extent ambition. In other words, I think we need to work towards the third objective. And there is no data set on the rate of calving and melting under the ice shelf for use by ocean, ice sheet, and coupled system modelers to better understand the processes, constrain the model, and ultimately better constrain our projections. And ocean ice in its coming activities will contribute to this. Of course, the flow of Earth observation data does not stop, and we need to stack this data to the one already existing to extend the duration of observation. And of course, at the same time, we need to improve our methodology, for example, by using field data to better validate satellite observation. And ocean ice will contribute to this as well. And you will have a presentation just after me by Keith Nicholls on our efforts in that direction. And on the long term, we know that ice shelves are Antarctica's weak point. We know that their evolution today is the trigger for the evolution of the flow of fresh water towards the ocean, with the possibility of tipping point being crossed, an entire region, particularly to the west of the continent, collapsing. So I believe that we need now to move towards operational and continuous monitoring of the ice shelf sanity. We need to progressively build early warning scenario. So thank you for your attention. And I'm going to stop sharing.
Thanks very much, Gaël. That's really very clear. And it's a really good introduction to our next speaker, which is Keith Nicholls from the British Antarctic Survey, who is going to talk about in situ observations and how these can be used with satellite data. So please, Keith, go ahead.
Okay, can you see my screen there?
Yes, we can see and hear you. So
Perfect.
Start.
Right, well, thanks very much, Gaël. That's a brilliant introduction. I'm going to talk about in situ observations of ice shelf basal melt rates. So this is a sort of complementary approach to the satellite or the EO's observations that Gaël discussed. And I also want to sort of explain really in more detail why we want to make those observations, how they're useful, and also an assessment of the limits, the present limits of those EO-sourced observations of melt rates and how we might be able to improve on them. Our aim ultimately is to create models of the evolution of the melt rates in response to climate change going out into the future. And this is a sketch on the left of your ice shelf with various sort of ocean processes going on beneath. And on the right, there's a map showing the distribution of basal melt rates on a large ice shelf in the southern Weddell Sea, the Ronnie-Filchner ice shelf system. This is a nice model, and it seems to do a pretty good job of giving a good melt rate pattern. So the yellow areas are melting and the blue areas are what the model thinks are freezing. But to project out into the future and to do a good job of this, we need to teach these models how to actually calculate the melt rates at the base. They're very good at moving heat and salt around, models, but they need to be told exactly how you convert those heat and salt data into melt rates at the ice base. And we can do that by drilling access holes through the ice shelf, making observations in the ocean near the ice shelf base, and comparing them with contemporaneous measurements of the basal melt rates themselves. And this is something that Ocean Ice has been doing on Fimble Ice Shelf in this previous, this last Antarctic field season. So hot water drilling, the holiday shots from hot water drilling, it involves lots of digging to create lots of water that you can then heat up, lots of heavy equipment, a lot of hose wrangling goes on, and sitting around waiting for the nozzle to find its way over a day or so through the ice shelf. And ultimately, we deploy these sort of fairly standard oceanographic instruments, but they're modified for use down boreholes, and they pop them down and they hang beneath the ice shelf. And we end up with a sort of a sketch like this in our heads. We have a logger on the surface, the borehole, a cable going through the ice shelf itself, and then the instruments hanging in the ocean beneath, in the water column beneath. And they'll be monitoring for some years the ocean properties. And at the same time, we have what we call an AP res, which is actually a downward looking radar, which bounces radar signals off the ice base and tells us pretty much directly how quickly the ice shelf is melting. And between these two sets of observations, the data from near the interface of the ice base and the radar data from the AP res, we can derive this sort of the transfer function between the sub-ice shelf conditions that are so well calculated by models and the basal melt rates. And here's an example data set from beneath Ronny Ice Shelf. In the top panel, we have, as a function of depth, set about 700 meters near the ice shelf base, and the seafloor is about 1,052 meters. And for a period of a year, this is showing data from 1 year. We have the temperature. This is the temperature signal. So red is and orange is hot, and the bluey color cold. And so near the ice base, it's cold. Near the seafloor, it's warmer, still about -2 degrees. And we can see there's a lot of variability going on through the year. And oceanographically, this is really interesting information. And the melt rate from the co-located radar, you can see beneath, responding beautifully to these temperature and also the velocity data that we had through the year. And the blue is the radar derived melt rate, the in situ observation melt rate, if you like. And the red is a sort of a tuned parameterization using the ocean data to get tuned by those melt rate data, just to show that we can actually do this. This is a technique that works. So we use the melt rate model, this melt rate data, to help us teach models how to calculate the melt rates. But we can also use time series to both to improve models, to tune models, and also to validate those results. And I'm talking about models here. I'm talking about ocean models that include sub-ice shelf domains. In Antarctica, deploying moorings in the ocean is an expensive and difficult process. So one way of doing it instead is to create these time series of basal melt rates from the radar instruments scattered around Antarctica and around the ice shelves of Antarctica, and we want to use those data to help keep the models honest, the numerical models, make sure that we can validate them and improve them. And to that end, there is an international program called Nicholls that is the idea of which is to collect time series from around Antarctica, Antarctic ice shelves, melt rate time series from around Antarctica, and make them available to the modeling community. And Ocean Ice is contributing here by trying to gather some of these data sets, gathering them together and making them available. Generally, we have this is a map showing where we are at the moment. We've got, I think it's now 11 nations actually of deploying instruments around Antarctica. These various ice shelves have been instrumented for various periods of time, from a month to several years. They don't need to be contemporaneous. The model will sort that out for us, but we just need to get as much coverage as we possibly can for as long a period as we possibly can. And that's something that's going on at the moment. So the question is that Gaël raised was how we use the satellite data. He explained how we can use satellite data for melt rates. So in principle, we don't need to go to the ice shelves and deploy these radar instruments. In principle, we can use satellite data, but as Gaël pointed out, there are various. It's a very, very refined product. There's a lot of assumptions go into it, and they're basically we're making as much progress as we can. This is a nice example of the pattern of melting and freezing that was derived from these EO products. The blue, again, it's the same ice shelf, the Ronnie Filchner ice shelf in the southern Weddell Sea. The blue here is showing where the freezing is according to the EO product, and the reds are melting. Now, what I'm also showing here are a set of, you can see these little symbols here show where instruments, these are the radar instruments, have been deployed around the ice shelf, and they show that to a degree basically the EO products are doing a pretty good job. Not perfect, but not bad. And just note that the AP resers were deployed for different time periods to the time periods covered by the EO product. So it's not a totally fair comparison. But generally speaking, the patterns from the long-term average melt rates from these satellite-derived products do a pretty good job. Unfortunately, well, it's great for models. This is a great data set to help keep models honest and to test and validate numerical models. But generally speaking, it's the time series, the variability in the melt rate, seasonal, even sub-seasonal variability in the melt rate, that is probably the sharpest sort of comparison for models. And this is something we're beginning to attempt to do with satellite-derived data. Now, these are 6 panels here showing 6 time series from, again, this is a satellite-derived product. Looking at the black line is showing the melt rate as derived from the satellites over the period from 1994 to a few years ago. And these particular time series were from locations. We've selected them from locations where we had these AP-Res instruments giving us direct measures of time series for certain periods of those times. And the red lines are essentially what we get from the radar. So you've got the melt rate here between -5 and +5. So -5 would be freezing, +5 is melting at 5 meters per year. And what we can see is that at the moment we're not doing a great job. The black line is a lot of variability in the satellite-derived product, and the bluer line is like a time average from this, or a sort of a smooth version of the satellite data. And the red lines are showing what the direct observations from AP-Res are, the direct observations from the in situ data. And clearly there's a lot of variability in the satellite data that we do not see in the in situ data. So there's a lot of work to be done. And there's one site 5, interestingly, which is in some agreement, quite a reasonable agreement actually. There it seems that satellite-derived data are looking pretty good. The other sites, though, for whatever reason, the other sites are not so good. So although with the long-term average, the very long-term average is good, the multi-year average is good, we do have some work to do to try and get the timescales as short as possible to see the variability at much like monthly or seasonal timescales. So what are the potential problems? One possibility is the modeling that Gaël mentioned about we have to model like surface accumulation and firn densification, and this is based on essentially precipitation models and firn densification models. That's one area that needs to be looked at to see if we're doing a great job there. And the other one is actually looking at the ocean itself. Beneath the ice shelf, we have a lot going on. Different density water masses are coming in and going out all the time, and they're varying the surface elevation as well. So one possibility to try and understand the snow accumulation and whether the snow accumulation models are doing a good job is to come up with another version of the AP-Res, much higher frequency, which is looking right at the upper surface, seeing how the snow falls, how it evolves, how the compaction evolves, and how the firn then densifies, and just to try and help those models do a better job or see how well they're doing. And we can also have, imagine, a buried system looking upwards as well. The other one, the other possibility, looking at underneath the ice shelf, and this isn't a comprehensive list of potential difficulties, but these are the ones we're focusing on at the moment. The effect of the density anomalies coming in underneath the ice shelf. So here's we have an ice shelf floating in the ocean, and then if we increase if we have denser water flowing in beneath the ice shelf, then in a very simplistic way, we can see that we can imagine that the ice shelf itself is going to float a little bit higher in the water column in the water because it's denser water, but the water itself is denser, so it actually effectively contracts under the ice shelf. So overall, the net result is the ice shelf floats a little bit lower in the water column. So these are the areas that ocean ice is so looking at, participants from ocean ice are looking at the moment to see how we can improve the results. So in summary, we need models to project to predict future basal mass loss due to basal melting. We used in situ data to teach the models to diagnose the melt rates from their data that they themselves calculate. And we've got a scheme to gather as many melt rate time series for validation from around Antarctica in place. And the holy grail is getting the refined, high reliability melt rate time series from satellite data, but that needs some more work. So with that, I'll stop.
Thank you very much, Keith. That was a really good introduction to some of the difficulties we have in reconciling in situ observations with satellite data. There's plenty of work to be done, clearly, in that. We're going to move now to Anastasiia Chyhareva, who is hopefully still sitting with electricity in Kyiv. And we're going to go back to the surface processes and to the atmosphere and to look at the effect of extreme weather events. And Anastasiia has only just started in ocean ice, so I guess this is mostly more plans but maybe some results too. But please do go ahead, Anastasiia. Would you like to try and share your screen?
Thank you, Ruth. Here, one moment.
Yes, we see it and we hear you. So please go ahead.
I represent National Antarctic Scientific Center of Ukraine under WP3 project, and this project started just recently, a few months ago. So here I would like to talk not about our results, more like about our plans for future and how we can contribute to Ocean Ice project. So under the WP3 project, we have several objectives, some of them very technical, like training and preparing and making samples in the Southern Ocean nearby Northern Antarctic Peninsula. And also we have scientific objectives like investigating characteristic structure of waters and exchange of waters in Weddell Sea and West Antarctic Peninsula waters. And another very important part of WP3 that I will focus here is examining the impact of precipitation on ice shelf mass budget by snow and rain using high-resolution atmospheric modeling. So because we were talking about snow and ice, but also precipitation and the characteristics can impact the ice and the snow balance significantly. So here's a task that we cover under WP3 project, and what we will be doing to study precipitation is providing some historical evaluation of rain and snow precipitation in the region, and also doing high-resolution polar warp simulation with regional atmospheric model polar warp that will be focused on some specific atmospheric events that will be possibly we will catch during the sampling in the southern waters. So our deliverables will be basically reports on these studies, and we are planning to have some analysis on historical evolution and some specific cases over the Antarctic Peninsula region. So to clarify here what we are also kind of planning to do, our task will be divided on two parts, like climatological part and regional modeling. So based on our previous studies, we will provide something similar. So it was assessment based on SMIP5 regional modeling of precipitations, their phase and intensity. On these slides, you can see that based on our previous research, we can suggest that the highest precipitation index and the highest fraction of rain in total precipitation actually is nearby Antarctic Peninsula region, North and West Antarctic Peninsula region, where we will be making samples during the next year with ocean ice. Also, we can assume that based on SMIP5 projections, the fraction of rain in total precipitation will increase till the end of the 21st century. That can possibly impact the mass balance in Antarctica significantly. Also, we were looking on fraction and total amount of clouds over the Antarctica. So here are some results on Antarctic Peninsula as well. And also we can assume, suggest that the total amount of liquid clouds will increase dramatically to the end of the century. At the same time, amount of ice clouds will increase comparatively not so intense. So this can give us some understanding of the processes that will be happening in the future and how we can be ready to these processes. Second part of our studies will be focused on specific extreme events that we assume that will be happening in the future more often. So basically on high resolution atmospheric modeling, as you can see on the screen. So we can use this information actually to follow in the details atmospheric flows and their changes in the region of Southern Ocean and Antarctic Peninsula. Having this information, we can also simulate how it will impact on sea ice, on mass balance. So hopefully this will be able to produce this in future. Here are some results on previous studies for extreme precipitation events, and we were investigating some vertical profile and vertical changes of atmospheric flow. Basically, having these results, we can assume the absence or presence of vertical movements, the extent of clouds in the air, and how it interacts with the surface layer. So you can see on these slides actually cross-section through the atmospheric flow, perpendicular to atmospheric flow, and through the Antarctic Peninsula mountains. So we can see actually how Antarctic mountains impact on the atmospheric flow, and how different could be impact of one atmospheric event from eastern and western side of Antarctic Peninsula. For this event, we were using for data verification information from the Vernadsky station observations, and for the first time from Vernadsky station since past 30 years, we deployed radio zonding measurements to provide us additional unique information about state of the atmospheric atmosphere. So to summarize our plans and our future work that will be done, so we will be focusing on precipitation, their time intensity, and their impact on sea ice and snow balance as a contribution to ocean ice with package 3. So work will be divided into parts: climatological assessment and regional weather modeling. And under the climatological characteristics, we will focus on precipitation type, occurrence, and the frequency of this extreme precipitation occurrence over the Antarctic Peninsula. For this will be used Euro 5 global reanalysis and the SMIP 6 Antarctic Cortex models that is provided now by different projects that focus on polar region, polar S. So additional second part of our assessment will be used polar dwarf regional atmospheric modeling with high resolution to investigate processes in clouds and precipitation that could impact on precipitation type, which in their turn can impact sea ice and snow mass balance. So thank you for your attention. Follow our work on ocean ice and National Antarctic Center service. Thank you.
Thank you very much, Anastasia. I think that's a really good comprehensive overview of the plans we have. It's going to be a lot of work, but it's going to be very exciting. I think that was all our talks for today. So we'd like to open up for questions. And I guess Griffith will probably moderate that now. So thank you very much.
Yeah, happy to do so. Thanks to all the presenters. It's a series of very good presentations. I would encourage the audience again to put any questions they have in the chat or to use the Q&A function, but I have the esteemed honor of asking the first one. So I would not be doing my job as a policy officer unless I asked, this goes to pretty much everyone, that if you're a European and you live quite far away from the Antarctic, how should the Ocean Ice Project impact policy making? How do you communicate this to less scientifically literate people who think of the Antarctic as something very far away and maybe not relevant in the day-to-day lives, not quite as important as more local issues?
If I can jump in quickly, I'm going to ask Gaël to give his point of view in a minute because I know he has a really good answer for this, I think. But I live in Denmark. We're very close to sea level here, to the extent that last year we had a big storm surge. And it's very clear that these events are going to have even more impact in the future. And I think, you know, in the past, Denmark was really not interested in Antarctica at all. It was too far away. When we did a lot of polar research, but it was very much focused in the Arctic. And I think that's really changing now. And so I would encourage policymakers to really think about the long-term future, because that is really what's coming for us now, is the melting of Antarctica is really something that we can already see happening here. But maybe, Gaël, you have a perspective.
Yeah, I fully agree. What I can add is it's that not only people that live close to the sea that should be worrying the evolution of typically the sea level rise in the coming centuries, because it will impact structures that are key in the way our society is organized. It's a bit. It will impact everybody. It will impact our general organization. It will impact the global climate. So definitively, what happens in Antarctica does not stay in Antarctica and impact everyone around the globe.
Good, thanks. Any other speakers feel like adding?
Yeah. Oh no, go ahead, Anastasia.
Thank you. I just want to add that we should keep in mind that Antarctica is kind of at the beginning of a huge chain of processes in the climate system of Earth. So if something happens significantly in Antarctica, it will reach everybody on our planet. We just should keep this in mind. Yeah. Thank you.
Yeah, and I just wanted to jump in and say, Antarctica is very far from Europe and it can feel very far away. And I think that we have a responsibility to figure out how to build connections with people, even when they can't go to Antarctica and can't see the changes that are happening. And I think this is where a lot of like communication and art and policy efforts come in, because you have to reach people at their like hearts and minds and communities, in addition to understanding what the scientific impacts are going to be and what those effects on coastal and inland communities will occur.
Yeah, thanks very much. I feel like you've just plugged the European Polar Board for us, because that's a lot of what we try and do over here. So thanks for that response. I'll just say that coming from a non-natural sciences background, the disproportionate importance and impact of Antarctica on global climate has kind of caught me by surprise. So it's a good thing to communicate. Let's see, we've got a question here in the Q&A. We've got two questions. In fact, one is they're from an anonymous attendee, but thanks all the same. They're asking, how is the uncertainty in melt rates calculated when derived from satellite products? And do these products also provide cross correlation between data points? And I'll read the second question. What will the temporal resolution of the climate simulations, or what will be the temporal resolution of the climate simulations for the Antarctic Peninsula? So some technical questions there for you guys.
I think maybe Keith or Gaël should take the first one.
Yeah, I'm happy to have a go at the first one. Gaël probably knows better than I do, actually. But like I said before, the melt rate estimates from satellite data are a very highly refined product. A lot goes into it. It's actually I think it's very clever the way it's done. And Gaël actually expressed that nicely with his sort of formula that showed the various contributions, and each of those contributions obviously has uncertainty attached to it. What the satellites do incredibly well is measure. Well, some of the satellites definitely measure very precisely the elevation of the surface of the ocean, of the surface of the ice, and so that is great. It's kind of the other and the velocity as well. Surface velocity do a terrific job. The problem areas and the ones that are really hard to nail the uncertainties for, as far as I'm aware, are the surface, the way the surface is changing. So the firn, I think Gaël expressed it as the firn air column, the amount of air in the column. So how light or how dense is that ice column, because that tells you how high it's floating in the water, and if that's changing, then that'll give you errors, and that is a real difficulty. And I don't know how, I must say, I don't know how the modelers do estimate that, the uncertainties there. The other uncertainty I discussed is one that's actually only cropped up quite recently in my thinking, at least, which is the one I mentioned about that's why I highlighted it, because it's kind of new to me as well. The changes underneath the ice shelf, the density. So the water, both eustatic and steric changes in the water column. So changes in density, changes in water volume beneath the ice shelf, which happen on oceanographic timescales. Those are uncertainties that really yet need to be nailed down. So it's not actually much of an answer, I'm afraid. All it really is doing is saying there's a lot of work to be done to get these uncertainties more precisely nailed down. So Gaël, maybe you have some technical sort of input.
No, I don't have more to add. I think what is definitively, it's obvious, great with Earth observation is the fact that they are global, but there are a number of assumptions behind, because it's not a direct measurement. And as you said, direct measurements, we are pretty good. Change in elevation, change in the velocities. But when you have to add hypotheses, typically on the firn and the density, you add you add mistakes, and also the variability is key. So no, I think I stop here. I cannot answer on cross correlation. I'm not enough in the analysis of the data to give an accurate answer. Regarding the second question, I'm not sure to fully understand what is behind temporal resolution of the climate simulation, but I think that usually stakeholders are interested in very short time scale, in the sense of a few decades, but I think it's somehow misleading. It's that the event, like extreme events, could trigger change that lasts for centuries. And typically a collapse of an ice shelf can happen in a week, but the consequences are here for centuries. We have to extend the way we think on the timescales, because there are some long-term planning where for sure Antarctica will be key for the change we will be faced with. Not sure I answered the question.
I think so. I'm personally quite fascinated with temporal resolution, but does anyone else have a comment on that?
Yeah, according to what we are planning to do under WISH-OE with climate data, so we will focus on decadal average, so like till the century of, or till the middle of century, till the end of the century, to understand the dynamic of changing in values that we are interested in. So.
And I think I would like, if I can add one point to that. I think Gaël is completely right that these changes can happen overnight, and suddenly, you know, we saw this with the Conger ice shelf in 2022. It literally collapsed overnight when we had a big heat wave in East Antarctica. But that ice shelf had been getting smaller and probably thinner. And I think it really indicates why we need a project like Ocean Ice that's looking at all these different components. So it's looking at the ocean that's melting from underneath. It's looking at changes to the precipitation from the top. It's looking at changes in the firn layer and the surface mass balance. And then the extreme event is kind of like this trigger that sets off this whole cascade of events. And so it's a really complicated system. And I think also this question about, you know, what is the uncertainties and the errors, this also highlights another important point that we're trying to deal with in this project, which is we just don't have enough observations, certainly not on the ground. So, you know, trying to understand what's happening actually at the surface in Antarctica is quite challenging. We actually have more weather stations in Denmark, which is tiny compared to Antarctica, which is a continent the size, almost the size of North America. So it's really a big challenge. And so having to fill in those in situ observation gaps with satellite data, and then finding out that actually we need to really be careful with the satellite data, or trying to fill in with models and trying to bring together this kind of different combination of in situ observation, satellite data and models. I think that's the only way we can really resolve any of these contradictions.
Yeah, thank you for the response. I'm going to piggyback on that slightly and ask another question that we've got, which is, what data sets are we missing to better understand these processes? And how do we get better support in terms of being able to make these observations in the future? This goes out to all of you again.
Well, I would like,
general.
you know, I work at a meteorological organization. Obviously, I want more weather stations, but I think that part of the issue is communicating that this is important. And yes, even if we don't have an Antarctic program now, maybe we should be thinking about how we can better support that sort of with international collaboration. But I think maybe Elizabeth, you should comment on this, because you've done a lot of work with the model outputs, and how do we assess which models are actually working?
Yeah, I think this is a big question, especially when we're running, I mean, we're running things to the present day right now. And then, yeah, how do we make sure that the same physical processes and observations are what's important for future models too? That's a really difficult question. Yeah, I think that Antarctic science is really hard because it's a really big place that's hard to get to and impossible to live on, basically. And so, yeah, the support that's required to get folks out to these places that are really changing quickly. Like, I was on a project that went to Thwaites Glacier, but it's, you know, you have an 11-day field season and you're in Antarctica for 3 months. And so it's these weather delays and logistic delays and just the complications of working at the bottom of the world are really quite significant. And I think the only way that we get there is through international collaboration and yeah, working together, projects like these that really bring folks from all different parties to look at these problems as one.
If I could just jump in with another comment. We talked this afternoon a little bit about how do we get satellite data to tell us exactly what we want, and clearly having satellite data covers pretty much Circumantarctic, and it's if we can have very strategically located measurements that will enable us to improve make the satellite data more reliable, not just melt rates, but more generally give them more reliability, give them better temporal resolution, better spatial spatial resolution is pretty good already, but and then in the same way as we try and do with models, so we're now becoming much better at targeting particular parts of Antarctica, particular parts of the domains that we're looking at, to make observations in places that the modelers care about. So the various locations that are particularly sensitive, grounding lines, for example, where the ice sheet's first going afloat, that seems to have been an area that's been highlighted by modelers over the last 10 years as being pretty critical to the way the grounding line of the ice sheet is going to evolve in the future. And so we've been beginning to be targeting observations into those areas. So it's not so much, it's not as much, no, we want more observations, but we also need to think very carefully about where they're going and make a real effort to get to the places that are going to leverage better, ultimately better data sets from satellites and also better performance from models.
Yes, and I just want to add that it's also important to have long-term measurements. And actually, our measurements are extremely short. Why are the projection of the contribution of Antarctica so poorly constrained? So let me try an analogy. If we were meteorologists, the question which is asked to ice sheet modelers in the community today is like if we were meteorologists asking to anticipate a hurricane in the tropics when we have only measured a small rain in Spain. You can understand that it's difficult, and it's basically what we are faced with. Because the system has such a long inertia, we need long-term measurements, and the observations are increasing pretty well in terms of number. Just have in mind that having roughly an idea of the velocity of the surface of an ice sheet is a bit more than 10 years. It's only 10 years. So we need to continue what we have. These are the basics things we need, but for sure we need more measurement on the ice shelf. We need to understand how the melt will impact the ice shelf. We need to better understand calving. We need to understand the circulation below the cavity, inside the cavity, and measuring something few hundred of meters and kilometers away from where we can access to is for sure challenging. So we need more, and at least what we have for longer term.
Thanks.
I completely agree with that. I think it's a great analogy as well, Gaël. I did want to just point out that the number of weather stations in Antarctica actually peaked around about the International Polar Year and has since been declining. And so in situ observations of certain very key variables like weather stations, we have to keep remembering that we need to keep them going. And maybe the next International Polar Year will help, preparations for that will help to keep up the visibility of this kind of work.
Yeah, and I'd like to highlight the role of international cooperation in making a lot of this stuff happen in such a remote and inaccessible region. Working together is always going to get better results.
I would be more bold than that. It's impossible without international cooperation.
One could say. So we're running a bit over time, but we've got such a good group here that I hate to cut it off short. If anyone has any other questions they want to put in the Q&A, otherwise I will say, bringing it back to the Ocean Ice project a bit more specifically. So where do you find the strongest links with the other work packages, and what do you envision the results? I mean, where do you see the results taking you after the conclusion of the project? I mean, what are your hopes and aspirations for where this project leads and how it opens up doors to additional opportunities or challenges?
I guess that might be my question first, but I'll try.
Yeah.
I can see Gaël smiling at me. So the most direct link we have is to the work package 4. So one of the basic things we're trying to do here is produce standardized data sets that other parts of the project can use in terms of evaluating models, but actually also later in the project assimilating data into those models so that we can try to get a better understanding. And this is sort of based on how weather forecasts work, in the sense that we take data sets that we have and we try and assimilate them into weather, or in our case, climate, ice sheet models, ocean models, and get better performance that way. I think we're still in the infancy of being able to do that because, you know, as we've said, we don't have enough observational data, and many of the models we have are also being under development. So there's a data kind of feed coming out of work package 3 that will go into the other projects. And I think ocean ice has been a really great opportunity for different European countries to work together and develop some of these common tools that we're all relying on, which will be a long-term sort of benefit from the project. And likewise, we have many really talented early career scientists, and I'm really pleased that we have so many of those into the project, and they're able to learn and make those kind of collaborations and international networks. So that, I think, will be a long-term legacy. But I would love to hear what my colleagues think.
I can try it. I think whatever the project we are mentioning, we should be humble and be sure that we will not solve the problem in 4 years. I think you agree, Ruth. This means that we need some continuity. And there is a great polar community working on Antarctica. It's also true for the Arctic. And I think it's always a pity that we have to reshuffle our community or organization each 4 or 5 years and be sometimes with a gap in between. So this is ice sheet study is a long-term process. So researchers need a long-term perspective to work more efficiently. And yeah, that's it. I will stop here.
I can make 1 or 2 comments that occur. I think Ruth used the word legacy, and I think that's an important word. So it is a short term. All projects are short term. 4 years is or 4 or 5 years is actually great by modern standards. No problems there. But what we clearly we need continuity. Clearly, as Gaël says, but thinking in terms of legacy for this particular project, there are some specific sort of fairly nebulous things, so not specific but nebulous things that help us. One is I mentioned Nicholls as this SUS endorsed sort of program for gathering data sets from around Antarctica. If projects like Ocean Ice can actually give Nicholls, which has been sort of hovering along, sort of not desperately active, but we can projects like this one, like Ocean Ice, can really give a shot in the arm to a project like Nicholls. We can help gathering data sets together. There's a renewed calls for those data, which actually help sort of galvanize people to get their data sets sort of made available to everybody else. So actually, there's this nebulous but sort of galvanizing effect that a very broad project like Ocean Ice can have, and I've seen that, and it's been really nice to see. But apart from that, there are legacy aspects that I'm aware of. Even just data sets that we are being gathered because of Ocean Ice that would never have been gathered to get otherwise. And one of the particular things that Ocean Ice is doing really well is putting a lot of work into gathering together. There's multitude of different data sets that are out there, and they're being gathered. I know that's the British Antarctic Survey, that you've got researchers doing this, and I'm sure it's happening in many other places as well. Within the program, where we're gathering together data sets that are really valuable, because all of these data sets are valuable because there's so few of them, but by gathering them together and making them available to the community, and this is absolutely key. Otherwise, if they're not in a relatively easily accessible form, then they're not worth having. We need them to be accessible and not forgotten about, and that is happening, and that I think is a very important legacy.
Thank you very much. I'll give people one last chance to put any questions they have, but I just want to touch on a couple of the points, one of which is the work of package 7, which will be coming up in a separate webinar, but that should hopefully talk a bit more about data accessibility and sharing. The data desert is a term that I've heard thrown around in some of the other projects that I think Ocean Ice is dealing with as well. And also just the synergies and cooperation, especially with the EU Polar Cluster that has a variety of polar research projects that Ocean Ice has a lot in common with some of them, and has worked together with some of the others. Ruth was kind enough to join us at a policy briefing in January at the European Parliament, where we talked about especially some of this more long-term monitoring. So this is a recurring theme. So these are hopefully all things that can be worked on outside of the more technical science, I guess, and into the future. And I think that there's been some good discussion on all that, as well as, of course, the actual science. So I am going to close us down here. We're getting close to our sort of maximum allotted time. I don't know if anyone else, any of the speakers, have anything that they want to add as a final thought. Otherwise,
I think if I may just say one thing, I think one of the really nice things that's come out of being involved in Ocean Ice and other polar cluster projects, since you mention it as well, is that it's really demonstrating that European institutions and our partners outside of Europe can work together really effectively. And I think there's a lesson for all of us in that, that when we have the opportunity, we can actually work together and get some really good science done. And that's been a really important and valuable thing to learn.
Absolutely. Good. Well, let me thank everybody. So thanks to Ruth, Elizabeth, Gail, Keith, and Anastasia, and to the audience for joining us. I want to also thank my colleague Eva Horochakova for her work promoting and coordinating the event. I certainly wouldn't be able to manage this on my own. And just to remind everyone that a recording will be available on the EPB YouTube channel in the coming days once we've downloaded and edited a bit. I'd also ask anyone listening to this to follow the European Polar Board and the Ocean Ice Project on social media, where you'll find updates on our future activities and events, which will include the next webinars in this series. We're hoping to have the webinar series start back up again after the summer and extend into next year. And then finally, this is the last webinar that I will be conducting on behalf of the EPB. So I'd like to thank the Ocean Ice Project and team for being extremely well organized, very interesting and enthusiastic group. And it's been a pleasure working with all of you. So I hope that we cross paths again in the future. And with that, I will say goodbye and have a wonderful summer. Bye, everybody.
Thank you, Griffith. We're going to miss you.
Thank you.
Take
Bye,
care.
everyone.
Good luck.
Thank you.